For example, you can use a crane in which you can mount a camera and look at something. You can use an aircraft that's fairly commonly used, or you can use a balloon. But the focus of this lecture will not be any of these. It will be on satellite. That's because satellite gives you the most comprehensive view of the world. The others give more detailed view of smaller regions. The satellite gives you a big picture, which is very relevant to climate change. In climate change, you want to look at the big issues. So I'm going to focus on that as the tool that's used for understanding glaciers and climate change. Now let's look at a satellite and what parts of satellite do the remote sensing. First of all, you need power, of course. Without power, you cannot run a satellite. So the solar cell is a must for any satellite. And then you have all the sensors. There are various sensors here. We'll talk about them in the next few minutes. And you also have to, after gathering information from the Earth, you have to communicate this back to the Earth. And for that, you need a separate antenna there, right, on the top. So that has to communicate information back to the Earth. And lastly, all these instruments are mounted in what is called a bus. Bus, all the electronics and batteries and everything. So this is the main structure of the satellite on which the solar cells, the sensors, and the communication antenna are mounted. Okay. Now, you must remember that when you launch a satellite, we typically talk about its life. Typically, life can be 3 years, 10 years, 15 years. Now, you might think that the satellite life is how long it remains in space. That is very, very long, because once a satellite put in space, for it to come down because of drag will take 50, 100 years. The real life of a satellite really is not to do with how long it's in space, how long can it communicate information back to Earth. For that, you need this antenna there. And remember that antenna is pointing towards a particular spot on Earth where there's a ground station which picks it up. Now, if the antenna angle at which it looks starts wobbling for whatever reason, then the satellite won't work. So most satellites stop working when their antenna, which is supposed to point towards the ground to a specific spot where it is collected, that pointing error starts increasing. That's called attitude, A-T-T-I-T-U-D. So a satellite has to maintain an attitude, that is a particular angular orientation, so that the antenna can point towards ground. If it can't do that, so many satellites after a few years start wobbling. Why do they start wobbling? You must remember that satellites are very often at some height, 800 kilometers, maybe 36,000 kilometers, and there are no force on the satellite. Satellite is in free space. Okay, there is a minor drag force due to air. Interestingly, the major force satellite is the solar wind. From the sun, these particles are coming, they are hitting the satellite, all these surfaces. So satellite will start slightly wobbling because of the effect of solar wind. Now, to ensure the satellite points towards the ground in the right spot, there are special engines, small engines are there, all the satellite, to adjust the attitude. So you have at least 6, 7, this one, at various X, Y, Z positions. So if the satellite is pointing in the wrong direction this way, you fire the engine this way, it will come back. So all these little engines, they are also this size, they are filled with fuel. Okay. Now before you launch a satellite, you have to decide how much fuel you want to put in that engine. As you all know, launching a satellite involves a lot of energy, so you can't go on increasing the weight. There's a weight restriction. There's only so much weight your rockets can launch. So you have to carefully decide, okay, I'm going to have this satellite for 5 years. So I put enough fuel in these small engines so that it can adjust the satellite's attitude for a period of 5 years. Okay. Now, sometimes you're lucky in this space technology. If you're lucky and the satellite is not subject to too much of, shall we say, bumping by solar wind, then sometimes satellites last 15 years, 20 years. One example is one I'll talk about later, the Typical rainfall measurement mission, one of the best satellites launched, the first satellite to carry an active sensor, that is a radar, and that was launched in 1998. Initially, it was designed for 5 years. It went on for 10 years. It went on 15 years. It died pretty much last year, 17 years. So they were lucky. So typically, satellite designed for 5-year life with all those engines with fuel in it. The fuel doesn't run out. You can keep running satellite as long as you maintain the altitude. That's the only requirement. Satellite will be there in the space a long, long time, 50 years, 100 years, but it will not give you information. Now, there are many, many satellites right now around the Earth, and they measure all kinds of things. This measures the sea level height. This measures, again, two sea level heights. It measures gravity of the Earth, measures rainfall. This measures clouds, measures aerosol. So now we have a huge number of satellites. As a matter of fact, this measures ice. So as a matter of fact, the challenge many of us face today is there's too much data. You go to the website of any of NASA or any of these, data is pouring like anything. Okay, the challenge is to how to handle the data coming in gigabytes and terabytes. So you have to know, the main challenge is not only to know which data to use, you must also know what are the limitations of data. The main problem today is, for all of you, there's all kinds of software available, all kinds of data available, but many of you don't know what the limitation of data in satellite is. To understand that, you must know how the satellite collects data. What are the basic principles behind it? Because sometimes you can misuse the data because you don't know its limitations. Okay? So the purpose of the lecture is to tell you the basic principles through which satellite converts what is measures to what you want to get, and what are the errors involved in that measurement, so that you don't use the data in situations where it's not really valid. Yeah. No, you avoid that. No, you should not. For example, if your sensor is there to measure sun, it will be there with sunlight. Otherwise, you make sure it looks away from the sun. Suppose I have a sensor in the infrared, okay, to measure the sea surface temperature. It shouldn't be pointing at the sun; it will be destroyed. So it's make sure you protect it. See, remember, most sensors of a satellite looks towards the Earth. Okay, only one sensor which is measuring the solar energy will look up. So you ensure those sensors do not get sunlight into it because it will be too high a load on it. It will become too hot. See, there are various in the sensor design, which I will not have time to talk about. There are issues of temperature control because a sensor cannot become too cold, because remember, space is a very cold place. It cannot get too hot. So you have to maintain sensor in a limited range. It is done by using various kind of reflectors, various kinds of protection. So you have to ensure, for example, suppose this is the satellite sensor, this is your bus, and you are mounting the sensor here. Now this sensor should not see a part of the satellite. It will be a wrong answer. So you put a certain shield here to protect it. So you have to ensure that the sensor is having a field of view exactly the region you want to see and nothing else. There will be. Let's say, let me tell you that when you design a sensor, you calibrate it. Okay. So this sensor, when it gives this kind of input voltage, what it is equivalent to this kind of let's say radiation. Now, when you put a sensor in space, after 1 or 2 years, it will get degraded. Okay. It is also hit by particles. So normal practice in scientific satellites is to have an internal calibration. Okay. For example, for sea surface temperature measurement, the sensor will look at the sea surface, then it will rotate and look at a standard source inside the satellite. Inside the satellite, there is a constant temperature source. So look at it, and that is a calibration technique. So you have to, if you want scientifically valuable data, then you have to ensure that your sensor is frequently checked for correctness. And this is especially true for climate change. Remember, climate change is a long-term change in something, right? So typically, suppose I want to know what is the change in sea surface temperature for the last 40 years. Okay, we have 40 years data. Now, one satellite won't give you that. because one satellite may last 5 years. So you have 8 satellites data. Now when you have 8 satellites, 8 of them have 8 sensors. They are all designed same way, but they are not identical. So what you have to do is you have to make sure satellites overlap each other, and in the common time period when the 2 satellites are running, you have to intercalibrate. It's a lot of work. It's a tedious work, but it has to be done. So now people have combined 8 satellites data by carefully looking at the overlap period, and if the sensor shows slightly different value, you adjust the values so that you have continuity of data. So this is a big challenge for climate change. For most of the time, satellites are used for weather forecasting. For that, you don't need calibration. Because the cyclone is gone, I forget about satellite. So that's what IMD was doing for a long time. But now, we are all using satellite for climate change understanding. For that, the demands are, I'll give an example later. To measure the Earth radiation budget, which is very important for climate change, that satellite costs $100 million. That's about 500 crores. And why did it cost so much? Because each of the sensors had to be calibrated to give radiation accurate to 1 watt/meter squared. That's not easy. Okay. A lot of work is required on the ground and in the satellite. Unfortunately, you don't have time, but if you have time, you can go and have a look at, ISRO has a center called ISAC, and there are whole floors whose only job is to calibrate instruments. Very lot of work is done for calibration, because you have to do first calibration at the ground to make sure everything is right before it goes up. Once it goes up, you have to calibrate in the satellite. So both are done. Okay. So remember that just to put a sensor in satellite, you won't get good data. You have to work on it all the time, because sensors do degrade. Okay, that's why sensors are expensive. That's why it is expensive. Technically, it can be complicated. And the main point is that satellite does not measure exactly what you want. Okay, it measures either reflectivity or radiation or backscatter, and you want to convert this into something you want. Okay. And the major challenge is how you convert, and what are the principles used in conversion, and what is the accuracy of that conversion technique. So this is the whole spectrum of radiation one can use in a satellite, going from the visible, this is in meters, so visible is somewhere here, okay, and all the way to microwave, radio waves, and so on. Entire wavelength is covered, and we'll see that each wavelength has advantage and disadvantage. General principle is very simple. If you choose low wavelength, that is high frequency. All of you remember, simple way to remember this importance. High frequency means high energy, because all of you know that the photon contains this much energy, right? So if you go to the high frequency part of the spectrum, that is low wavelength, you get a lot of energy from that photon when it strikes your satellite. So you will get very good sensitivity. So you can detect very small things if you want to detect. But remember that if you use visible part of the spectrum as your energy source, it's good. It's a lot of energy, but unfortunately, you won't get data during night. I want to measure sea surface temperature at night, of course, not possible. Then you have to move towards infrared. Infrared has a slightly lower value of frequency than visible, so less energy is available. So when less energy is available, either your sensor has to be more sensitive, or you have to average over a larger area. So when you do a satellite measurement, you have to make a decision over what area you want to average your data, and that depends on how sensitive your sensor is. So if sensor is not very sensitive and the energy coming is not enough, you increase the area in which you do the coverage. Now finally, people also use microwave. Microwave is very high wavelength, so very low frequency. So energy is very, very little. But microwave is still popular. Why is that? Because one of the major challenges we have in India is you want a lot of data about sea surface temperature and water vapor and things during monsoon. During monsoon, there's a big cloud cover over India. Right today, you can look at it, clouds are covering most of India. Now, if cloud is covering ocean and land, then you cannot see the surface in the visible or in the infrared. In both regions, clouds are completely covering the Earth. The only way you can look at the Earth's surface is through microwave. Microwave penetrates clouds very easily. Okay? But unfortunately, microwave has very little energy. H0 is very, very low. Okay? about 1 millionth less than what you get in visible. So when you go to microwave, the only compromise you make is you average over larger area. So we'll see later on, whenever you have microwave data, the resolution is not very good. Typically, what we are getting these days is 10 by 10 kilometers. For visible, I can go, like what mentioned by Kiran Kumar yesterday, can go to 1 meter, half a meter. But you can't do that in microwave. Microwave will be in kilometers because it's got less energy. Okay, just a little history. First satellite for weather application, climate application was launched in April 1960. That is 55 years ago. And the first geostation satellite, which I'll talk about very soon, was launched only in 66, less than 50 years ago. Okay, and this has, of course, revolutionized weather forecasting and understanding Earth's climate. And so last 50 years of data we have to look at. So there are two main kinds of satellites launched in the last 50 years. One is geostationary, which is very high above the Earth. The other is polar orbiting. This is most common. Most satellites, 95% are of this kind. Typically over 850 kilometers above the Earth. And this is much, much higher. Now why is this much higher? Because in a geostationary satellite, you want the satellite to rotate around the Earth at the same rate as the Earth is rotating. By doing that, you ensure that satellite remains stationary with reference to a point on Earth, right? If the satellite is over Bangalore and is going around the Earth once in 24 hours, then you'll see Bangalore and nothing else. So to ensure that, you have to go to this altitude. Let me just show you how that is done. That's purely from simple Kepler's laws. So this is the geostationary orbit. Around the equator it goes. The equator of the Earth, and is going around at this altitude. Why this altitude can easily be explained by a simple formula. And for that formula, I'm going to assume the Earth is a sphere. Earth is not exactly a sphere. You can see there's a slight difference in the radius at the equator and in the pole, but that will small difference, you'll ignore it. If you ignore and take Earth as a sphere, then you can calculate from Kepler's laws that the period of the satellite is proportional to the gravitational constant, mass of the Earth, the distance between the satellite and the center of the Earth, and you can calculate this quantity. Okay, and this example is given here. If the satellite is at the height of 360 kilometers above the Earth, this is the Earth's radius. You can calculate this. It will have a typical 91 minutes, typical polar orbiting satellite, about 90 minutes. So typical satellite which goes around 500 to 800 kilometers above the Earth will have a 90-minute orbit. Okay, that's very common. If you want 24-hour orbit, you have to take the thing much higher, and all of you can calculate this. You put here in 360, 36,000 kilometers, at once they will become 24 hours. All of you can check this very easily. Okay, this is a comparison between geostationary and polar orbiting. Okay, now remember that geostationary satellite has to be along the equatorial plane. So you can imagine that now every country in the world which has got some interest around the equator have got their satellites. So there's lack of space here. There's only one plane in which you have to put satellites. So now there's the international law. It determines who will put a satellite because there's not enough space. But polar orbiting, no problem. You can put any angle here. Huge coverage is there. Okay? You have a lot of space to maneuver here. Here you have no space to maneuver. So by law, India has a right to put satellites between, I think, 70 east and 100 east. And then China and Japan take over 100 to around 150. Then America, being a big country with huge, this one goes on from whole of Pacific and America and Atlantic. And the Europeans control that Atlantic to 70 east. So the whole world is divided into 6 or 7 zones. Each country is given, and Japan also covers that side. Each country is given certain space, and that's all. So that's how it is done. Yeah, this example of satellite here, inside is not mentioned here somehow. So around the equator, these are the American satellites around Pacific, the European satellite around Africa, inside should be here. Then this is the Japanese satellite, and one of inside is here, I'm sorry. that is here. And this is the Japanese satellite GMS here, and there's a Chinese satellite here. So all these are covering the equatorial plane. Now, typical polar orbiting satellite, one advantage of polar orbiting satellite is that the geostationary satellite is very good for looking at a point continuously, cyclone tracking and so on, but it cannot look at the poles. You can calculate the distance of the satellite is 36,000 kilometers from the center of the Earth. You draw a tangent, it will not go much beyond some 50, it will not cover this region. Okay? So polar region is not covered. So if you want global coverage, you have no choice but to go polar orbiting. There is no choice. Okay? So most satellites are polar orbiting because a typical polar orbiting satellite will cover most of the Earth in 24 hours. Because it takes 90 minutes to one round. In the meantime, Earth is rotating. Satellite will cover different part of the Earth in the next 90 minutes and goes on like this for 17, 18 orbits, and will cover most of the Earth. Okay. So these are the most popular satellites. Secondly, of course, you must remember energy required. The energy required to launch a satellite into geostationary is very large because you have to go to that MGH, that height you have to go. Polar orbiting costs much less because it's only 800 kilometers. So most satellites are polar orbiting, a few are geostationary. Yeah, this example of one of the satellites the Americans launched earliest. So it has a visible resolution of 1 kilometer, which is very good for studying clouds. Infrared has less energy, so a little more area is required, 4 kilometers. And I'll talk about this later, sounder. So these two are the typical image sizes we get from geostationary satellite. But if the same sensor is put on a polar orbiting satellite, you can get even finer resolution because you are nearer to the Earth. So here he has got both 1 kilometer. You can actually can go below 1 kilometer. Infrared comes to 1 kilometer, but today even less is possible. You get 500 meters, 200 meters, and so on for measuring sea surface temperature. Okay, so this is the typical track. So satellite is moving like this. You look at the point right at the bottom, that's called the nadir. So nadir track is shown here for geostationary and geostationary you are showing the field of view, and for polar orbiting you are showing the nadir track. So you can see it starts here, goes many rounds, and ends up finally here. Okay. So it covers the entire Earth in many orbits. Now this is what is shown here. The line is the nadir point, and remember that when the satellite is going like this, if you want to cover all portions, you have a scanner which moves like this. So if you move like this, you cover a certain portion. So depending on how far you move to the right and left of this nadir point, you'll get a coverage like that. So I'll show that in the next slide. Yeah, this is a comparison between two satellites. This is polar orbiting, and this is TRIM, Tropical Rainfall Measurement Mission. The TRIM's main aim was to study rainfall in the tropics. So they decided to reduce the inclination. It was not polar orbiting because in the poles it doesn't rain much. So the inclination was 35 degrees. So that satellite only went up to 35, 40 degrees. Well, the polar orbiting goes up to the poles. Okay, but notice that the TRIM satellite covers the tropics much better than the polar orbiting satellite because it is most of the time only in the tropics. So there is a comparison between two kinds of satellite tracks here. And this is megatropics. It was launched 3 years ago. And here is Bangalore, one ground station. The other is Kororo, the French station. And it was launched at inclination 20 degrees. Again, it covers only tropics, 20 to 20. And you must remember that satellite, when it is going around the Earth, is gathering data. Now, that data has been downloaded. So you need a ground station. So there are two ground stations here. That means 90 minutes you're collecting data. So every 45 minutes you download here and here, roughly, 2 places. Okay, or can download all the data in both places. And there are a lot of technologies involved here. Remember, the satellite is going over, in the case of here, not Bangalore, but Hassan. Hassan is the tracking station for ISRO. It will go over that place only in a few seconds. So you must have a very special way to rapidly download data of 90 minutes in a few seconds. That's a challenge. Quickly you have to download all the data in a short period when it goes over Hassan, because the time will take only a few minutes to cross that region. So this is one of the challenges in satellite data. Remember that today with very special instruments available, I can get a lot of data. But that data has to be downloaded to the ground in a short period of satellite goes over the ground station. So that limits how much data you can gather. That is the biggest problem. If you are very particular, in some satellite what they do is, they, as the satellite collects data, it's put on a tape inside the satellite, and then slowly it is downloaded to the ground in many rounds. That also can be done. But remember that there are constraints on how much data you can transmit. Okay, this is a view of 7 days of orbit of megatropics. And you can see it only covers part of India and this one, because we want to understand the role played by clouds in the tropics. So our focus was mainly this region and not this or this. This is the 3D view of the same thing. Okay, so just gives you the various regions used in satellite, visible region, infrared, and microwave, and various bands in the microwave. And the key point to be remembered is that Earth is fairly opaque in the infrared, fairly transparent in the visible, and in the microwave. So if you want to study the Earth's surface, then you have to stick to visible or microwave, or a small region here around 10 micron, which is transparent. It's called the window. There's one window here, another window here, a big window here, and a large window here. So these are the windows through which you can look at the Earth's surface. So you can ask, what is the use of this region, which is completely opaque? This region is useful if you want to study the atmosphere, because in this region, atmosphere absorbs Earth's radiation and re-emits it to the satellite. So satellite can only find out what's happening in the atmosphere, not the surface. So that's also useful. Remember that satellite is not only used for Earth's surface. That is also used for studying the atmospheric temperature profile, humidity profile, profile of carbon dioxide, amount of methane, amount of ozone. All these you want to measure, then you will use the absorption bands of water vapor, of ozone, of carbon dioxide. So if you measure the amount of a gas, then you have to look at these absorption bands. If you want to look at the Earth's surface, you look at the windows. Okay? So that's the difference between these various channels. This is a typical view of a polar orbiting satellite for one day. What you must remember is that this is called a swath. This is the nadir as the satellite moves, and it scans this way. So it moves this distance. Now in this satellite's case, this is Terra, the movement are such that the next pass of satellite and this part, you don't know, overlap. There's a slight gap. You lose information there. There's no choice. Okay? So you might say, why not increase the angular movement of the scanner? The problem is, as you go to larger and larger angles, this I can best show. Unfortunately, this is not working. I don't know why it's not working. All of you can imagine, take your any light source, put it right on the nadir point, it will be a circle, right? As you move away, it will become the ellipse. As you move very far, the ellipse gets distorted, and the data you get is not very reliable. So you cannot go beyond 50, 60 degrees. If you go beyond that, the data you're getting is highly distorted data. So most people restrict the scanning this way to around plus or minus 60. So that is the limit, and that is, and R is the edge height of satellite. So h into this theta is what is the maximum you can go. So they have done that here, and the slight gaps are that, which is missing data. Here is an example of trim coverage. This is 1 day and 2 days. You can see in 1 day, trim does not cover all parts of the Earth. There's a gap. But you go over 2 days, it covers all parts of the Earth. So typically trim is used not for daily data, but for average over 2 or 3 days it is safer. Another satellite, this is, okay. In polar orbiting satellite, there are two kinds. One is sun synchronous and other is not. What is sun synchronous? You make sure that your orbit around the Earth is an integral multiple of 24. Now why is that? For certain applications, like ocean color monitor, you want to look at the same spot every day at the same sun angle. Because sun angle determines how much it is reflected from the ocean. So the ocean color is very important. You want to know where the phytoplankton are, where are the fish going to be. So you want to know where the ocean really producing a lot of photosynthesis. So for that you look at the ocean, the visible region, and in the visible region you look at the ocean with sun coming at a certain angle, let's say 9 a.m. So today you look at 9 a.m., tomorrow also should be 9 a.m. so that you get the correct picture. Tomorrow is 11 a.m., you get a different reflectivity. So these satellites are so arranged such that they go around the Earth, let's say every 1 hour or every 2 hours, so that when you divide that by 24, you get an integer. So that means I'll make sure it comes back next day at the same time. Today it's 6 a.m., tomorrow also 6 a.m. If you don't make it an integral multiple, if you make it some odd number, then it will come today 6 a.m., tomorrow 7 a.m., day after 8 a.m. So then it's no good. So this is very easy to arrange when you launch a satellite. When you launch a satellite, you adjust the altitude such that its orbit around the Earth is a round number divisible by 24. Okay. That's what you do. Okay. But this satellite has also lots of gaps, you can see. This is microwave satellite. Okay, so this is an example of the scanning. So the nadir point scans this way. If it scans right at the nadir point, it will be like a rectangle here, slightly at a different angle, so it is slight arc is there, you can see that. So this is how satellite is moving, and it is scanning this way. But scanners are a problem. History of satellite technology has been, the scanner has a moving part, okay? And in the conditions of space, it's very cold there and harsh, the scanner can fail. So as a matter of fact, megatropics on a scanner failed. So generally, if you want reliability in a satellite, you should not have moving part. So what can we do? Unfortunately, if you want to cover a lot of ground, you need scanner. But today, there is a revolution. All of you have a mobile phone with you, and it contains what is known as CCD, charge coupled device, which was mentioned yesterday by Anil Kulkarni. Now that's a small, nice electronic sensor, and that's become very inexpensive now. So what you do today in satellite is, instead of scanning, you put lots of these CCDs along the line here, okay? And then you move this way, that's all. No scanning. This is a beautiful solution. So this will work forever, as long as satellite is there, because no moving part. So you have small sensors arranged all like that. But you can imagine all this is a very elegant solution. There's a problem. You have to make sure that this CCD and this CCD has the same sensitivity. You have to calibrate it, because there are so many of these sensors now, let's say 100 of them or 50 of them, all the 50 had to be identical. So there is a lot of lab work to make sure that they're all identical. So a lot of money is spent in space application. You'll make maybe 10,000 pieces and you'll select only 100, because they have to be identical, right? So that is the challenge here. There are, in this scanner, there is only one sensor and you're scanning. So no problem with calibration. Same sensor is saying all parts. Here, there are 100 pieces and it is moving this way, very nice, but you have to make sure that all these are giving the same response. Yeah. Yes. Yeah, that is true. At nadir is the best resolution. As you go away, it will get more and more distorted.
How do we calibrate it? I mean, for the same image, we will have the same pixel resolution.
So what you generally do is, At nadir you get the nice little circle, okay? Now as you move away, it becomes ellipse. Now what you decide is, you make a decision. Let's say this is, just for argument, let's say this is 1 by 1 kilometer here. There it is 4 by 1 kilometer. And you want uniform result. Then you make a compromise. You say, I will make all the data 2 by 2 kilometers. So you give 2 by 2 kilometers here. There you'll have 4 kilometers. You have to somehow overlap two of the images to get you have to do some averaging there. So always near the end there will be a problem. So no, you reassign. What you do is, here you have 1 by 1 kilometer, right? And as you go away, it becomes larger and larger. But the user wants data in a uniform grid, right? So you average it such that 2 by 2 you get lots of data, but near the end you won't get 2 by 2. You have to make some assumption and approximation to interpolate from 4 by 1 to 2 by 2. You have to do some little careful thing you have to do. So at the end always there's a problem. So generally we avoid, I try to stick to plus or minus 30. That's very safe. But if you go to 60, problems are there. Yeah, CCD is very good. No, everywhere everything is same. But then you have to worry about all giving the same data. Yeah, CCD is much better. Yeah, this is called the push broom scanner. So it's moving this way, along track. Not, this is called cross track scanning. This is along track scanning. So if you have a CCD camera and you push it like that, then you're covering a rectangular space with no problem. Yeah. Yeah, could be, but I tell you the general experience in last 50 years space technology is avoid moving parts. So you want a moving sensor at the end, it may fail sometime. Why do you want to take the risk? See, I tell you why you is, if you are so particular about not having gap, you make a longer sensor, that's all. What is the problem?
So those cases which for polar orbiting sensors, they missed a few parts.
Yeah, that's because these are old satellites. In a new design, what you will do is, if you decide you don't want to miss any point, the length of this should be such that the next pass will overlap with this one. You can design it. The design stage, you make sure the length of your push broom is such that the next pass which comes here will have at least 1 or 2 CCD overlapping. You have to do the design stage.
Or else it is just extrapolation.
Yes. Or interpolate. What happens is you have data here, then you interpolate. It's interpolation, not extrapolation. So what's happening, I tell you, in the old days, people were happy with whatever data came. Now the user community is getting more and more demanding. So people are getting more and more fancy, and there are no more, I don't think any new satellites have any gaps. Gaps have been pretty much removed now because people won't tolerate it, but they want data everywhere. Yeah, just give you an example before I go into more detail. This is an example of how using both microwave and radar, people have been able to monitor the movement of ice, which is a major theme of this course. So this is possible today because ice and water have very different property, both in the visible and in the microwave. In both these regions, ice and water have very different properties, so you can exploit the difference very dramatically. And people have been watching, and one advantage of ice, remember, it moves very slowly. So data once a day is more than enough. While clouds is very difficult. Clouds in megatropics, they were very particular about data every few hours, because clouds last only at the most 1 hour, typical cloud. So if you want to understand clouds, you have to have very frequent sampling. But ice is safe. It's a very slow moving stuff. You can get data every week or even someday every month for a glacier. So a lot of good data has been obtained from microwave sensors in the last 40 years. And for example, what you saw yesterday in my talk of the decline in Arctic sea ice from 21,000 to 8,000 was all done by microwave satellites. You go over the poles every time, you know exactly where the ice line is, you mark it, and next time you go, you mark it, and you get a very good idea about how it's moved. Here was the famous example 13 years ago when the Antarctic Larsen shelf collapsed. Okay, this was seen by satellite. When it started collapsing, this was seen very clearly because satellite was over it when it happened. Now, one of the challenges in satellite remote sensing is to differentiate between cloud and ice. It's very tough, and I think Anil or somebody will cover that part because clouds reflect radiation invisible, so does ice, so does snow. Snow, ice, cloud, they are very similar in characteristics. So you do a lot of careful analysis to separate out this. Here you can see roughly that there is fog here and there is ice here, and you have differentiate between fog and ice. I think here the fog is a little darker than ice, I believe. But sometimes they can be same color. Then you have to use some other region. Yeah, this is fog, darker one, and ice is this. Huh? No, this is not microwave. This is visible. I'm talking visible here. Let me tell you what channel it is. Nova 12. So this is visible. Yeah, microwave will penetrate the cloud. Yes, microwave no problem. You'll see this one. But microwave limitation is you do not get high resolution data. If you want high resolution, you have to be in visible or IR. Yeah, microwave will go through cloud, no problem. If you have large glaciers, microwave is the best. Yeah, so here is a clear distinction between water and ice, which we have to make if you have a cloud, you want to know whether it contains ice or water, you have to know that the refractive index, write down, the refractive index determines what happens to the, so N has two parts, real part, which all of you know about. So this determines how it reflects, this determines how it absorbs and emits. So this is absorption and hence emission. This determines reflection. Okay. So look at the imaginary part of water and ice vapor index. You see they are very similar in most places. Very similar. Okay. A few spots they are slightly different. And you have to exploit. So this 11 to 13 micron will be talked about in this course later. There's a clear distinction between ice and water, and so is true around 6 micron and around 3 micron. So these are the places you put your sensor to differentiate between ice and water. Okay. So suppose you want to know ice cloud or water cloud, you have to use those wavelengths. Yeah, the other thing you are using very often in the microwave is to differentiate different land types based on their emissivity, okay, at nadir. This is the frequency in gigahertz. You can see that microwave is very useful to differentiate between ice, dry snow, refrozen snow. All these can be differentiated because they are slightly different emissivity at some frequencies, and this is wetland. So you can choose the right frequency to differentiate between wetland and seawater, or between dry snow and refrozen snow. So these are information you require to be able to identify what kind of landform you have. Here's an example of the global land emissivity product from the 37 gigahertz channel of SSMI, and you can see clearly that areas which have snow have much lower emissivity than areas which have water. Okay. These are land, these are dry land mostly. And what month is this? March. Okay, March, most of the area is dry, and most of it is snow covered. So you can see the differentiation in emissivity very clearly there. Yeah. Huh? This should be, microwave will be typically, and 30 gigahertz will be most like 20 by 20 kilometers. It won't be better than that. Huh? Yeah. Which frequency? Depends on frequency. See, if you go to higher frequency, you get, see, remember H nu. Nu becomes higher and higher, you get smaller and smaller pixel size. Which frequency you are talking about? That's very important. This is 1000 gigahertz, this is low frequency. Because now in microwave I have 183, which will give you 10 kilometers. What is it you are talking about? Which one is this? Huh? No, inside not microwave. Inside is geostationary, cannot be microwave. See, the geosatellite is at 30,000 kilometers. It cannot use microwave at all. It's too high. can only use visible infrared. Okay? So microwave, so far only polar orbiting satellite carry microwave sensors, because you know that radiation goes 1 over r square. When you are at a height of 36,000 kilometers, there will be no signal available for microwave. Very tough. Although there is some research going on, maybe in the next 5-10 years they'll put up a satellite, but it's going to be very tough because the signal is so weak at that altitude. Only visible gives you a good signal. Yeah, just to give you the idea of the footprint of satellite, I've given 3, I don't know whether you can see all of them. The this cross-track scanning, okay, swath is 2,200 kilometers typically, and first I want you to look at blue, okay. The blue is MSU, very old satellite, microwave sounding unit, launched about 30 years back, I think. This one, it has a huge footprint, not a small one. Then AMSU came. It had a much better sensor, bigger antenna, so it became green. Okay. Now, final one, how many of you can see at the back? I don't know. That's the red dot. That is the size of the pixel of this gun. Okay. So it's very small. So as you get the pixel size depends not only on the frequency, it also depends on the antenna size. If you put up a huge antenna satellite, you can collect more energy. But as you can imagine, typical satellite is of this size. You can't make antenna bigger than the satellite, then it will be unstable. So there are challenges there, but today, as mentioned by Kiran Kumar yesterday, there are synthetic radars coming into play. Maybe they will avoid this physical antenna requirement. Okay. So physically, you want to put antenna, you have to put a huge antenna to collect a lot of radiation. Yeah. Huh? But how do you downscale? What is the principle? You have to make some assumptions. See, anytime you downscale something, you have to make some assumption, and that does may be wrong. Downscaling is like interpolation. It's always risky because you make some assumption about how things are varying in between. So if you want accuracy, you better go for high resolution right in the beginning. Yeah, yeah. But you come up with a number in between the very low resolution of resolution here. But in that, what I mean that you are compromised. You have to interpolate.
So I was thinking it will downscale those low resolution pictures into high resolution pictures.
But you see, you must remember, once you got data with a very poor resolution, you cannot. The information you have has gone down. You have nothing to do about it. You have to just hope that you can interpolate and get some answer. But you are compromised by, see, suppose the pixel at the end is about, let's say, 10 by 30 kilometers, okay? Now from there, you can't get 1 kilometer data, no chance. You can make an assumption. If you know something about, for example, in the case of sea surface temperature, which varies smoothly, I can make some assumption. But you take clouds, I can tell you, you cannot make any assumption. If you take 10 kilometers by 20 kilometer pixel here, it may only be partly cloud covered. You don't know. How do you interpolate? So it depends on what property you are trying to get. Things like rainfall and clouds are very dangerous thing to handle because they vary a lot. But things like sea surface temperature, water vapor, they are very smooth variation. I can assume a nice medium and will get the right answer. That's why all of you must know what is that you are trying to get. So if you are trying to get a quantity which is smoothly varying, then you are lucky. If you have a quantity which varies rapidly, then you are in trouble. Yeah.
We also know the resolution of the images that are taken with two angles.
Yeah.
So if we will try to downscale them with the same resolution.
No, how do you don't know? The point you are missing is how do you downscale? Because the point I'm trying to make is, this is the nadir image, okay? This is the image at high angle. Now, suppose this particular image is partly covered with clouds. How do you know that? You cannot know that, right? But if it is SST, no problem. SST very smoothly. Assume that between this point, so you have this data, and you know average here and here. You can in between you can interpret, no problem. But there are certain quantities like rainfall, clouds, aerosol, may vary a lot spatially. So you have to have a resolution for that, no choice. So remember, it all depends on, there are some applications where people happily interpolate, do all kinds of tricks. It's okay because that variable happens to be smoothly varying. But there are some variables which are not smoothly varying, then you cannot downscale. Okay, now let's come to details of the sensor. So in a sensor characteristic, you have to decide in the beginning what kind of resolution you want, horizontal and vertical if you are measuring the vertical variation also. And you also want to know how frequently you want sampling in time, okay? And what wavelength you want to use, that depends upon what you're going to measure. And what instrument noise you're willing to tolerate, you have to decide on that. What calibration you're going to take, at what rate data is coming in, because that will depend on how you download the data. And how much time you're willing to wait, latency time between when it's collected and when it comes to you. And for climate application, long-term stability of the sensor. And then this is a new problem. See, today microwave is very popular because you can look through clouds. Unfortunately, all of us have mobile phone now. That also emits radiation in microwave. So satellites are having problem with that. It is measuring a microwave emission, not what you want to measure. There's a cloud there whose reflected I want, but unfortunately I'm getting your signal. So this is a huge challenge. So there are negotiations between the telecom companies and research people. Telecom people want more frequency. All of you want to use more and more data and more time. And so the telecom guys are demanding more frequencies, while the scientists are saying, no, don't give it to them. We want to keep this for scientific measurement. So the big debate and trying to avoid this frequency interference from human devices. And of course, there's always a problem with space in the aircraft. Remember, no spacecraft has enough space. You have to put so many sensors. There's a problem how much you can accommodate. And you have to worry about mass. You have to worry about how much power you have from the solar panels. So very major issues. Well, finally, of course, don't worry. Don't forget this part, cost. Final decision is made based on cost. Because cost is always a constraint in any space mission. So most of the sensors that are used are passive sensors. That means they merely pick up the emission by the earth or by the atmosphere and so on. But today there are more and more active sensors. Active sensors are where you send your own signal and it comes back. And active sensor is very expensive because you need a source of power in the satellite to send the radiation. And so it's expensive and reliability is not very high. So they are not used that much as passive. So, so they have been used, already mentioned by Kiran Kumar, scatterometers. You send a beam and it scatters from the surface, you measure the amount of scattering. So used to measure sea surface height, because you know the time the signal takes to hit the sea and come back. From there you know the height of this one. It is used to detect rainfall, vertical distribution in trim. Aerosols, which Satish will cover, I think. And today even you can look at winds in the atmosphere by active sensors. And various moisture profiles also used using kinds of LiDAR and so on. So these are all now new sensors coming up active, but they are very expensive, so they are not used that often as passive sensors. Now sounding is a word to use when you want to measure the vertical distribution of something like temperature or moisture or CO2. Okay? There you are focusing on the earth, but the atmosphere. So you want to divide the atmosphere in various layers, and each layer emission. So what's happening is the principal layer is different from looking at the surface. I think, okay, I'll put it here. So this is the atmosphere, let's say. There's various layers with various temperature, various humidities. Each layer is emitting radiation to the satellite. So use different wavelengths to take care of different layers. Okay? So if you want 10 layers, use 10 wavelengths. Each wavelength is so chosen that most of the radiation comes from that particular layer. Okay? This is called sounding, this technique. So for example, INSAT 3D has a humidity sounder. So it has many channels. Each wavelength is chosen for one layer in the atmosphere, and it will give you the exact distribution of humidity in the atmosphere. Yeah. These two are the most common pairs. And actually, today the whole new technology all of you know about is GPS. There's a clever technique, totally different. See, all the other approaches here and here depend on ability to sense the emission, absorption, or scattering of the atmosphere or the surface. GPS is completely different. GPS doesn't care about that. GPS merely is a way to look at the atmosphere by measuring the delay in the signal sent by the satellite as it goes through the atmosphere. So as it goes through the atmosphere, the signal, it will bend. Why it will bend? Because refractive index is a function of space. Okay. All of you know from mirage and so on, that if n is not a constant, n is varying, the ray will bend. And the amount of bending tells you what is there along the path. So this is a very clever technique, requires no calibration, because you're merely measuring the change in the speed of light. That's all you're measuring. You're not measuring absorption, emission, nothing. So this is very powerful now. Technology is very inexpensive. That's why it's there in every mobile now almost. So this is a new technique which is going to become more and more important, all because we are able to measure the speed of light very accurately. I mean, that the accuracy is mind-blowing. I can't even imagine it. 10 to the power of minus 9 seconds. None of you can imagine what that is. Okay, they can measure it that accurately. So they have clocks in the satellite, on the ground, all calibrated, so they all accurate to 10 to the minus 9 seconds. And then you measure small changes in the speed of light. So this is a very amazing technology. I don't have time to discuss. Some of that time maybe if you want to give you some references. No, in active sensor you are looking at scattering of radiation you are sending. In a passive sensor you are looking at scattering by sunlight, for example. See, sunlight is a natural source, right? So many instruments use scattering by the sun's light, by the earth, by clouds on the surface. In active sensing, you choose the frequency you want to send. That's the main difference. Not necessarily, because sun is quite energetic. See, in active sensor, how much energy it has depends on how much power you want to put in a satellite. You remember, satellite has a laser, it requires energy. You need to collect the energy from the solar cells. So there's some limitation, you can't put any more energy you want. So yes, there is some control over the beam, you can make the beam very narrow, that's why a laser is used. Take a very narrow beam, intense thing you can send. But sunlight is quite good, sunlight is pretty energetic. What did we say? No, pixel resolution, you can make it even better for active sensor, depending on what is the source of the light, how powerful it is. But still, they're all around 1 kilometer. Nobody has gone to very high resolution yet, although there are some military satellites, which we don't know about, which go to half a meter, we don't know what they do. So if you go to military satellite where money is not a constraint, you can put any amount of money and radiation. Okay, I'll skip some of these, and because I think I'm running out of time here, right? 10 o'clock is the, yeah, so I'll just close it to somebody. There are more details here, which you're going to cover in the rest of the lectures, I think. Yeah, some of these I put there, but I realized it will be covered by Anil about snow mapping and so on. I'll just skip all that. This is a typical antenna using microwave. There are two antennas here, depending on the frequency. This is a typical antenna used in megatropics also. Yeah, this shows various ways in which surface reflects radiation. First one is like a mirror, and the others are rough surfaces which reflect in various directions. This can be used in your, and this will be covered by Satish. Aerosol remote sensing will be covered by Satish. So these all have covered, I think. Yeah, now there are modern satellites which are called hyperspectral, which also was mentioned by Kiran Kumar. Now there are satellites having 2000 wavelengths, 2000 different wavelengths. So you get huge amount of data. And the way you analyze this is very different from what we used to analyze multispectral or 4-5 wavelengths. So this is too much information actually, a lot of information comes in. So you use very fancy optimization algorithm in which you try to take all the information in and to find the best solution. So this approach you take here and here are very different. because there is so much data here. For example, let me give an example. Suppose I have 4 wavelengths here in multispectral. 4 wavelengths, 4 unknowns. Okay, you have 4 equations, 4 unknowns, you solve it. Now in that case, there are 2000 wavelengths and maybe 20 unknowns. Think about how will you solve it. There are too many equations and too few unknowns. So there are techniques available in maths. When you have so much information available to you, you use not the traditional inversion of matrix, but you use some of the optimization package to come up with the best solution when you have so much information with you. Okay, that's a whole new method. Yeah, this I have covered, and okay, this is all a lot of stuff. It will be given to you for your general details. I will not cover now. So that's the general view of remote sensing. Satellite is getting data of emission on the surface, a reflection from the surface, emission of the atmosphere. So which one you will look at depends on what you are measuring. When you see surface, then you focus on this ray and make sure all these are not important. If you are measuring atmospheric emission, then you want this ray and you want to ignore all the others. So how you design your sensor depends on what is that you are trying to measure. So that is the key thing in remote sensing. Yeah, this is a view of the rotating mirror. This is your push broom scanner. Yeah, one important thing I didn't mention, most important thing which we don't do, but done by the space people, is when they give you data, they have to ensure that it's properly registered. That is, when I say this pixel is at this lat and this long, the accuracy of that has to be guaranteed by people in space. They have to know the exact height of the satellite. Remember, satellite height changes. The whole scan thing will change, right? So we are continuously monitoring in the ground station the exact height of the satellite and correcting everything. So all this is done to ensure that every pixel is correctly registered at the right lat long. When you have a high resolution data like 1 kilometer, your satellite position has been known very accurately. So that's a lot of work which we don't do, it is done by somebody else. But be always alert when you use data. Sometimes there's a mistake. And if you are careful, you can find the mistake and tell them that the data has slight error in location. Yeah, this is one orbit which I normally mention to students. This is a very unusual orbit used by Russians. If you are in Russia and you want satellite hovering over Russia, it's not easy. Because geostationary doesn't reach there. Okay? So use a very highly elliptic orbit, and by laws of Kepler, when the distance is very far away, it will have the lowest velocity, so it will remain there for a long time at this. It will remain for a long time at this point. Okay, because that is a very long distance. So Russians use this for their mobile coverage in Russia. They can't use geostationary like we do. Okay, I'll stop here, and a lot more stuff than what I covered, because 1 hour is too short for this lecture. But if you want, you can look at more information here. Thank you.
How are we doing this? Okay. Okay. Are we ready? And you can hear me. Okay. Now I will talk about two main topics, or I will talk about the transformation of snow to ice. I mentioned yesterday that glaciers are made of snow. They are not made of water which has been frozen into ice. And then I thought it was useful to start to tell you already now some basic concepts about mass balance and flow. There will be later on a special lecture on mass balance and another one on flow, but it is useful to start to mention this early on in a course in glaciology. So now we are back to this this figure which you saw yesterday, and we are looking into what is going on here when snow is falling from the sky down onto the surface, and snow is accumulated on the surface and changed into ice, and this ice will start to flow. So this is the part of the game we are looking at now. And I will just start by telling you some basic concepts, some basic terminology, and you have just to believe me. You will or accept it. I'm making statements, and you will understand more of them later on. But I am making the statement that glaciers form by accumulation of snow, and the snow is a conversion of snow to glacier ice, and I will explain after this statement how this happens. And then the second statement is that the mass which is accumulated here on top of this ice mass will start to flow down due to gravity, due to its own weight in a gravitational field, which is and it will start to flow down. So in this picture here, you will see what I am talking about. I am talking about accumulation of snow in the highest part here. When we talked about snow line, we were talking about mountains. That was in the lecture yesterday. I was saying that snow is accumulated above a certain snow line, and we use that term snow line when we are talking about mountains. But when we are talking about the simpler term on glaciers, we use the term firn line. And you will understand. Or you could also say snow line on the glacier. It doesn't matter, but if you just say firn line, people know that you are talking about glaciers. And so above a certain elevation, snow will be accumulated and left at the end of the summertime. Now this snow will start to change, and there are several processes taking place. Some of them are, you can call them mechanical, they are thermodynamic, dynamical, and I will tell you more about that. And this snow is then gradually changed into old snow, and the old snow, which has survived one summer, is called firn. And at the end of the summer, we have old snow all over this area, and therefore it's convenient to talk about the firn line, down to the firn line. So first we talk about snow, and then it's changed into firn. But then some processes continue in this material, and the firn will be changed into ice. And I will tell you how this is taking place. And then the whole thing is starting to move due to its own gravity. It is not, this material, if you pile it up like that, it is not strong enough to withstand its own weight, so it's going to deform and move down. It's not a solid rock. It is a material which can deform. And here you can see the flow lines of what is produced of material here in this part is going to flow along the flow line and come to the glacial margin here at low levels. But here in the middle of this area, it will follow another flow line. Then, in addition to that, we have two other terms. We call this area above the firn line the accumulation area. And I said yesterday, nowadays glaciologists might not like that term, but we have to accept it because it's been used for a century. So accumulation area is another term for this upper part here, and the ablation area is the lower part. And now on, we can come back to this. So here we have a glacier, and at the end of this winter, it's completely covered with snow, and this is accumulation. And this accumulation is, and when we start to do computations, we call this C for the C here in accumulation, either capitals when you're talking about volume, but if you are talking about how many meters in a specific place, you use the smaller letter for that. And accumulation is any addition of snow and ice to the glacier. It can be snowfall, just from the sky. It can be wind drifted, for example, from the top of the mountains down to the main ice body. which is very common. It can be avalanches, just falling down from the mountain slopes onto the glacier. It can be freezing of water. It's not only snow, but when precipitation during the winter, in some parts of the world, we have even yes, precipitation moving over the glacier and falling down onto the cold surface, and the meltwater freezes. So this is accumulation. And then at the end of the summer, we have had ablation. And ablation is any removal of ice and snow. And normally, most of the ablation is melting. There was a question, very good question yesterday, what is the difference between ablation and melting? And I said, ablation is everything, melting is just the change from solid to liquid. Because we can have a loss of mass by wind erosion if snow is blowing off the glacier during the summertime. We can have calving, we talked about that yesterday. That is a loss of ice mass into the ocean. And we can have sublimation, especially on tropical glaciers. Sublimation means that the ice is disappearing from the glacier straight and became from the solid phase straight into the vapor phase. So it's not going through water, the water phase. So it's just, and so in this case the air has to be very dry and cold glacier. But, well, in Iceland, where I'm working, I don't see much sublimation. But you can see it in the mountains here, I'm sure. So it's mentioned there. Now I'm going to go in some details through the 1 year of one glaciological year. We call it glaciological year. It's a balance year. It's similar to the hydrological year. It's from the autumn through the winter and the spring and the next summer and ends in the autumn. The hydrological year is often from September to September, and that is just for bookkeeping. We don't use 1st of January for bookkeeping in glaciology. Of course, I'm not in hydrology. So it's the same way of thinking. So let me now go slowly through this. I have mentioned the accumulation area here and the ablation area. So this is the same figure as you've seen before, but let's now follow this stick. We start in an autumn, T1 autumn. Then the glacier surface has this. This is the surface of the glacier. It's a solid line going down here and down to the number 1. So this is autumn. We sometimes call this the summer surface. In glaciology, when you read the literature, this is said to be the summer surface. It's at the end of the summer. Now comes the winter. And the next spring, after a lot of snowfall, we come back to the glacier, and that is the spring And, and then the surface of the glacier is higher. It's here at the top here. A lot of snow has been added on top of the glacier, or the entire glacier, all the way down here and to there. So this is illustrating the accumulation during the winter. So there is accumulation everywhere on the glacier. And then starts the ablation. And then we come back at the end of the summer, and then we are in the autumn here. Then something is left in the upper part of the snow which was collected here during the winter. So we are down here, and we are above the initial surface. So this is the surface now. So we have gained the difference between this line and that line in the upper part until we come down to this area here. Then it's so warm that all the snow which was accumulated during the winter has been melted, and not only that, some of the and still more removed from here because it's a warm place. So now we end up with this surface of the glacier here number 3. And so this is the autumn. And now we see many interesting things. We see that there has been a net accumulation in this net addition to the glacier here in the upper part, and this is in the so-called accumulation area. But the reason why I don't like the term accumulation area is because we have accumulation in the wintertime all over the glacier. So this should be called something like net accumulation area, because we have accumulation. But okay, so this is the area where we have net accumulation. And so we can say that when we go down here, we have a loss. So there is a net ablation. So the ablation is higher than the accumulation. So we are losing mass in the lower part here. And this is the area which we call the ablation area. So in that area, the ablation is more than the accumulation. And here, at the boundary between those layers, we have 0. There is no gain and there is no loss in exactly this point here, and we call it the equilibrium line because the glacier is in equilibrium. There is neither gain or loss, so it's called the equilibrium line. We can also call it the Fern line, but the reason is that there is a reason why it's called equilibrium line, and that is because later on we will see how this is computed. And but the Fern line, on the basis of observations, mass balance measurements, But the firn line is something you can just look at the glacier from an aeroplane, and you can see a line with snow, and certainly, and from this you can see the firn line. So there are three terms here, and we will come back to them, all of them. What happened here? Well, there is something missing. Then I will introduce a term. We had talked about accumulation, ablation, but another term is a balance. And the balance is the accumulation minus ablation. And something missing. It's my fault here. But anyway, the balance in a certain point at the glacier, here or there, would be the accumulation in that single point, which will be all this up to here, minus the ablation, which is this. So what is left is a difference, only this, which is the B. So this is the balance, what is left. So we talk much more about the balance than the accumulation, ablation. We are interested in the balance of the glacier and the mass balance, and there will be a special talk about how that is estimated. We can give this for specific points, and therefore this is called the specific mass balance. But we can also integrate over the entire glacier, over a larger area, and then we use capital letters, and then this is a volume, and the unit here is volume per year, volume of water, and this is volume, meters of year. And it's in glaciology, we always change this over to water. It's not, so when we are talking about the volume, the mass balance, we have converted the value into water. Meters of water, cubic meters of water, because cubic meters of snow can be anything depending on the density of the snow. So we have to give the numbers in. Okay, so then now we can see a glacier just from the sky. You can see here that well, maybe I should just go back and tell you one thing. You should be aware of that this snow is changing into firn and then into ice, and when it is appearing here at the base, then it's made of ice. So you have snow in the upper part of the glacier, or firn, but at the end of the summer, the lower part is made of ice. It's gradually changed into ice, and when it emerges at the lower part, it is made of ice. And okay, so this is, here you can see only snow, ice. So you are in the ablation area. And here we have this. We can see that this is a picture taken at the end of the summer. In the upper area, you see snow. Then in the lower area, you see ice. There, the mass balance is negative. Here, the mass balance B is positive. And I'm drawing a line here, which is the equilibrium line altitude. And it is frequently used term what is the elevation of the boundary between the accumulation area and the ablation area. And you can see this from if you are just flying over and making a line like that, I would say, well, this is my guess of the equilibrium line, but I admit that this is the firm line indeed. I saw it from an aeroplane. But later on, we will see how this can be calculated based on measurements in the field, and then we use the term equilibrium line altitude. Now, sorry? Surface? Oh. Okay, the surface of a glacier. No.
Surface is horizontal, snowfall is there, the snow converts into the ice. How can we calculate this accumulation area?
Okay, so I will have a
Here it is elevation is there, so it is easily moving, and slope is there. But in surface area, there is no slope, and new snowfall is coming, and old is going into ablation form. How can we calculate?
Okay, I will just then I will just make a point. We will come back to that, but all the figures I'm drawing have a very much extragated vertical scale. If I were to draw a picture like that in the scale 1 to 1, it would be like that. And so you wouldn't understand anything. But of course you are surprised about the slope. But we are talking here about maybe 10 kilometers and 1 kilometer. So the slope or 100 kilometers or whatever. So, but we will come back to the calculation. So I would be happy to discuss and think about that later. So, and but now I'm going to introduce a term, and then change the topic over to how the transformation takes place. I just want to introduce a term called balance velocity. This is the glacier, and if it is, and we have a net accumulation here of B above this line. And it has a surface area of this. And everything which is accumulated on top of this area will flow by a flow line down into the glacier here in the accumulation area and down to the ablation area. So if this is a cross-section here beneath the equilibrium line, then we can estimate the average velocity of the glacier in a very easy way just from the mass balance. Because the product of the net accumulation in the upper part over the times the area here will be equal to the average velocity through the cross section times the area of that cross section. And this is the average velocity in a vertical cross section between beneath the equilibrium line. And this is what we call a balance velocity. If this is in steady state, it will just be moving. There is more added. There is no accumulation. So this is the most simple way of making a guess about the velocity of a glacier. And it's called the balance velocity. And if the glacier is moving at this speed on the average, it is able to transport what is accumulated on top of the glacier, and then it is in equilibrium. Of course, if the glacier is growing, if there is more accumulated here, the glacier is not moving fast enough to do this job, and it will grow. And that's what happens in climate deterioration. And nowadays, when glaciers are getting smaller and smaller, the velocity is lower than the balance velocity. But it is a very often used term. What is the balance velocity of the glacier? And so this, we can also do this just in a cross section like that. And then you, instead of using areas here, you just say you have a thickness, and you are assuming one unit thickness of this slab, and the balance is there. You can say integrated over a distance from a certain ice divide, just high up in the glacier, and it must be equal to the average velocity over this height. So I'm putting this in at this early stage because there is an exercise, I think, before we, later in the week. So, but it's so easy to understand this based on what we have been talking. Sorry.
The velocity that we are calculating here
Yeah.
is actually the shift of the equilibrium line with the time.
Actually,
It's the shift, the moment of the equilibrium line with the time. Is it like
if the equilibrium line is changing,
it's changing with the time. So is that the velocity here?
then you are making this more complicated. So I'm just introducing this idea, but
No, I'm telling that the velocity which we are calculating here,
yes.
that can we get actually from the shift of the line, because equilibrium line is shifting with the time. As accumulation and ablation will change,
Yes.
all this will change, so equilibrium will always shift. So is that actually the velocity that we are incorporating here in the formula? I just want to know that.
Well, this is one measure or a guess of how fast the glacier is moving. Yes.
That's what my question is actually. How can we know the velocity? What actually the velocity depicted here? Is it the shift of the line, equilibrium line? What's the velocity?
What is the velocity?
How can we know the velocity?
Well, I will show you in an exercise. I think it is the day after tomorrow. How we calculate.
No, sir, I'm talking actually the velocity. This glacier is moving down the slope. So when accumulation and ablation ratios they are changing,
Yes.
at that time also the ELA will shift from one place to another place.
Yes.
That's how we know whether the glacier is retreating or it is advancing. But in that way, I'm saying that when equilibrium line will shift,
Yes.
so we have the proper time that we have, for example, time is fixed for us. 1 year is there. So in 1 year, the equilibrium line has shifted from this to this. Can we say that it is actually the velocity because this is the distance covered by the glacier with respect to the time? So can we say it is the velocity at that time?
So it's the velocity which is changing.
That's
No.
what I'm telling. Velocity, how we can measure. That's my question.
Okay. Well, I can tell you that what I am. If you write the continuity equation, I don't know what. The change in the thickness of the glacier with time is equal to the balance minus the dq dx. So the continuity equation, if you take into consideration what is that the glacier is changing with time, then you have to look at the mass balance in a place, the flow towards there. But what I am doing is just to say, as a first guess, we assume that it is not, it is a stationary problem. So I'm making a, what is this? This is the flux with distance, is that? So what is? Okay, so this is the flux. You have an input. Q1, Q2, and you can have a change in dH, dt. So yeah, well, this is the flow of ice in and out of a box. Is that okay? Maybe we will then come back to it. Okay, I will do better. But okay, sorry. Are you in? Have you been studying some hydrodynamics or? Sorry, yeah, sure. No, but you have some
Some papers regarding AR and ELA I have read.
Okay. But we will have a special talk about all this later. So I was just.
Especially I am focusing on the mass balance only in regulation.
Okay. But we come back to this. I was just going to, I hope I am not stealing time from others here, but I will now go quickly through the change, the processes, how you transform snow to ice. What happens when snow is falling, that you have a very dendritic form of snow stars, which are, but then they will start to change with time. And this is an example how a snow grain, after 2 days like that, after 2 weeks, 50 days, you can see how it's getting rounded. After some time, 60 days in this example, it's just a small piece. After 90 days, it's become a cluster of snow grains, and finally it's ice. And just some pretty pictures of what we call in my country Christmas snow falling from the sky changing gradually over to solid ice. And here is some more of that that you can look at. And well, this is shown in a Polaroid polarized light. But anyway, it's getting coarse and more coarse. And in the beginning, when snow was falling, it might have, in calm conditions, it might be very light with density of just 1 or 10% of pure water. I mean, this is 100 and water is 1,000. But if it is windy, the corners may start to break off mechanically, and then you can get 300. You know that pure water is 1,000, but it's a very light material. But then there is a thermodynamical process taking over, and that is called diffusion. And this diffusion is the transport of molecules. They can either be in the solid state, and now I'm talking about snow, which is below the freezing point. So it's cold, and there is no melting, and it is also called dry. And you see the term metamorphism. It's borrowed from the from the geology, where rocks are changing with time, and they call it the metamorphism. And you can look at snow as a sediment, which is gradually changing with time into a solid rock. So the terminology is often the same. But it's done in two ways. The molecules start to move from the corners of the flakes. This is thermodynamical. They're unstable and aggregated here at the corners, so they start to move away from these. This has to do with surface energy along the surface, and this is called surface diffusion. And they can also move inside the flake, and then it's called volume. It's inside the volume. So this is one way. So they are moving away from the corners. But this snowflake is surrounded by vapor. And molecules are also moving in the vapor phase. And they are moving from the corners into the concave parts where they are settling down. This has to do with thermodynamics. The pressure in the vapor is higher here than it is there. So you get transport from all of the corners into, and this is going to make the snow flake more like a sphere. If we look at the snow pack, which is contained of many grains, they will start to compete with each other, and the result, one of the results is that larger grains begin to grow at the expense of smaller ones. But if you look at this collection of snow grains, and the smaller ones will have higher pressures in the vapor, and the the molecules will be moving over to the big ones. And so they lose all the corners and they get more and more rounded. And the result is that they become spheres of similar size. And then the density has been increased to 5,500 kilos per cubic meters, which is almost a little more than half of what water has. If we now allow melting, then this is called wet metamorphism. But you don't need any melting. But you know that this is very much depending on the temperature. If you are living in parts of India where snow is falling, and then you know that if it's really cold, the snow doesn't change at all. It can be can stay for days dry and blow around. But only a few degrees warming, even though it's below freezing point, will speed up the process, so the snow will become coarse. So, but if you get melting, then you will still speed up the process. So then water will be moving in between the grains and washing away the corners, and then you may get a refreezing during the night, and we call this internal accumulation. So it might be melting on the surface of the snow cover, but it's frozen again down in the snow, and that is called internal accumulation. It's internally in the snowpack. After this, when you have spheres of similar size, the next process is packing of the grains. If you have ping pong balls, they are all of similar size. And the perfect packing is that this one is located here in the middle of underneath those two. If it was straight over here, you would have a lot more space in the snow packets than if you just move this, all these layers here in the lower part. So they are located and fill up as much as possible of this space between in the upper row. Then you will get the spheres as well packed as possible, and it's called a perfect packing. And then after that, you will get more and more snow accumulated on this, and you will get deformation and the load. So there's a load coming on top of this and squeezing the spheres together. And what is now done is called sintering. That's a technical term, and what it means that they will be glued together, these spheres. And in the end, they will be closing off some air here in between. Air bubbles will be, so the air is not able to move anymore within the snowpack. It's located in isolated air bubbles. And at that time, it turns out that the density of this mass has become 830. That is our experience. And then we call this material glacier ice. This is called glacier ice. You can, by increased load, reduce the air bubbles and thereby increase the density of this material, and you may even reach the density of ice without air bubbles. Ice as you make in the freezer if you freeze it slowly. But anyway, these bubbles are in the beginning triangular in shape, as you saw here. So triangular in shape, but they become more rounded or elliptical, and they are very important in glacier studies because they contain examples of the atmosphere when the snow was transformed into ice. So they are keeping information for us about the chemistry of the atmosphere, and we will hear about that. So we know the CO2 content of glaciers 100,000 years old from these air bubbles. The density of the snow is increasing with depth. And here you see a graph from Greenland for a rather dry place in Greenland. And this is 0, and here we are coming down to 80 meters. And at 80 meters, the density is close to 830, so you are into what you call glacier ice. It takes a long time, and 80 meters of snow, of accumulation of snow to produce ice, glacier ice out of this. But if you go to a warmer place of the Earth, the rate is much faster. And we are here at 10 meters, 20 meters, seeing densities of glacier ice. And then okay, yeah, well, it's just a cold or dry metamorphism is slow process, but wet and warm when you have melting. It will only take a few years to produce a glacier ice. There's an empirical formula about how density changes with depth. It's an exponential curve, which is there. So it's changing exponentially, slower and slower here with depth. And I just put this, it's an empirical, and you'll get all the lectures so you can. Then I will just mention, if I have time, a rather different type of metamorphism. And that is a special form of crystals which are called depth hoar. And they are formed where you have a very steep temperature gradient. And I'm mentioning this because they are causing avalanche dangers. And if you have a hot surface of the ground, and suddenly, or wet, I mean, it's just at the freezing point, and then you get suddenly a very, very cold spell then you will start to get transport of molecules up from the hot to the cold, and you will start to form large cup-shaped crystals, which are called depth hoar. And they are very weak, and very much different from the types of from the snow crystals which I've been talking about. They may cause avalanche danger, and sometimes they may form on a glacier, on the surface of a glacier. If the glacier is wet, and you suddenly get very, very cold weather, 20, 30 degrees minus, then you can see them forming because the heat flux is out of the, but then they will be buried during the winter time, and you will never see them again. But you can see them in the mountain slopes, and they can cause hazards. You have a thin layer of snow on the mountains, and depth hoar might have been formed in the autumn because the ground was warm, and then suddenly got very cold snow. So you can get a layer of them, and they are very weak and cause avalanche dangers because they are not strong. I have a table here about the density of snow, and I'm not going to talk about it. You will get it in your. You can see that it's going from very light. So it's a typical values. Depth hoar, which I was mentioning, has a density like that. Windpack, fern over there. And finally, you get the ice with 830 to 910 in this table, and you can look at it yourself. And then the question, just briefly, how do you measure density? Yeah. There will be more about that when we talk about. You dig a pit into the glacier, and you take a container of given volume, and you push it into the snow cover. You know the volume. It might be 1 liter. And here is the snow, which you got out of the cylinder, which you pressed into the snow bag and filled it with. You put it into a plastic bag and you weigh it, and you read 550 grams, and you know this was 1 liter in volume, so the density is 550 kilograms per cubic meter. So it's a very easy way. Because of the.
And we are forcing some containers into the ice.
Well, you have to be very careful. Oh, yes.
We are applying some pressure, so the density will definitely be.
Well, yes, you have to be experienced to do this very carefully. You can also cut out with a knife a certain box of a known, yes. And when you put this into, you have a cylinder like that, And you know, I'm not going to push it further down like it's 25 centimeters long, and I'm not waiting until it's full, because I'm just putting it 25 centimeters down, even though it's half. So that's why I avoid your problem that I'm compressing the snow and filling the container with. So I'm not filling it. I'm just putting it 25 centimeters down and accepting that as the sample. I know that if it might be compressed while I am pressing it into the snow, but I am aware of that, and I'm as careful as you about that. So, okay. Yes. 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 Well, you can okay. You can do if you are drilling into an ice core and you get a core all the way to the bottom. You have a sample of the ice and you can measure the density of that. That's one way. You can also, here in the well, you take quartz here. I mean, it's easy to measure it in the accumulation area. But here, if you want to know the density of this, well, you can have a quarter and drill and take up a sample of, and you measure somehow the volume, and then you do the same thing of weighing it. So that has been done, and the result is that you're pretty much close to 900 wherever you are here. It's more variable in the snow. Well, it's, as you say, see here, it's an exponential curve. And it is rather, it's approaching here an asymptote, well, this value, or maximum value, so it's almost constant here for the rest of. So it's not increasing after, it's just approaching as an asymptote a value of 900. So estimate the density. Age, yeah. Not really by, no. Well, no, I wouldn't use density measurements to estimate the age of the ice, but we can come to that later. How you estimate the age of the glacier? There are several methods to do that, but I wouldn't do that by measuring the density. Carbon is one, yes. Oh, yeah. Sorry. Carbon. Yes. Oh, yeah, yes.
And then by using the
Yes. Okay. We will come back to that problem. It's an interesting problem how you measure how old the ice is. And, but I wouldn't use density. I wouldn't be happy to do it just with density. So come back. Yes. But you can, if you take samples of the air bubbles there, you can use them maybe for by chemical analysis of them, estimate something about the age. I think I will be thrown out soon, so I have to. But okay, this is a very refreshing job to measure the density of ice. You can see here we have a cylinder, and it now contains snow. We put the snow into the plastic bag and we weigh it. And this is it. I will just mention that the crystals, in the end, that the crystals, they grow larger and larger when they move down. It's not only that this is changed from snow to firn and ice, but the ice crystals grow faster and faster. And you can see some cross sections, how they are from this depth down to this depth have become larger. And there are some empirical equations, and you can find them in the textbooks, that the diameter of a crystal is depends on the diameter at the time 0, and will grow. The diameter square will grow proportional with time. And in the end, you can see in the lowest part of the accumulation area, you can see crystals which are as large as footballs. They can be of that size. It started as a snowflake, has changed gradually, and now it's a big bowl. So this is this is it. I just want to end with this, and you can look at it yourself. It's from a textbook of Patterson, and you can find on this several terms. Here is the ablation area, and wherever on the earth you can find some of these zones in a glacier. In the driest part of the world, you have the dry zone. You have no melting at all. You have never any melting. Then you are here. You come to lower elevations, and you get some melting, and the melting is going to percolate into the snow. So you are into what is called the percolation zone. But this will freeze again in the uppermost part. But when you come down to this level, the refreezing has been heating up the glacier. We will talk about that later, and eliminating all the frost, so it's completely wet. So the snow is completely wet, which means that it's at the melting point. And then you come down to the snow line, which is the firn line. And further down, you're approaching the accumulation area. But here again, you can get complications about this. If you are melting snow and it's refrozen into solid ice and staying there over the summer, then it's called superimposed ice, and it is part of the snow from the last year, which has now changed rapidly into ice and stays there. So it's not, so it's different from what I was talking about, the slow transformation. So this is called superimposed ice, rapidly formed ice. But now I'm just mentioning this as some details. And that was it today. And tomorrow, something else. And then we have practicals later this week, and then we will discuss some problems also. And also, if you have some questions. Okay. Well, is it tea? Coffee, tea? Okay, okay. Yes, yeah. And you are very curious, and I...
Adjacent to our office, our village office, so you can meet him and discuss with him.
Yeah, yes. I am not dangerous, so it's just no.
Let us have it.
Okay, okay. No, I'm happy if you have questions. And
I would like to meet you in that case because I am also planning to work on the master plan for Glacier.
okay.
The first thing PhD, and I have selected one Glacier. Actually, it's brilliant.
Oh yeah.
This it is there. You just dispose this. Yeah, उसको थोड़ा okay, close the door. Everybody has come or okay? Good afternoon to all of you, and this I will start my lecture. This is partially misnomer, this title, because I will talk many other things, because since it is the first lecture, but eventually it drives towards development of algorithm for estimation of snow cover in the Himalaya. But since yesterday or today you have series of lectures which talk about remote sensing techniques, electromagnetic radiations, its wavelength, and which region is reflecting, which region is absorbing. And top of that you have talk about satellite sensors, different satellites, how their orbit changes, all those things you have talked about it. But now, when you have this huge amount of information, key question is what you do with that. And from the huge number of the satellite sensors and its characteristics, we will pick up one satellite sensor, which is built by India and whose design was prepared by the man who has come here yesterday, and it was manufactured by him also. So Kiran Kumar who was here yesterday. So we will discuss this thing and how we will use different characteristic of sensor in our analysis. That is what this lecture is all about, and it will help you to realize how we are going to treat, why understanding of satellite sensors, its specification is necessary for doing decent scientific work and reaching to the logical conclusions. But let us look into the issue to start with. Differently. How many of you have seen the snow and ice? Okay, and how many have not seen? Almost everybody has seen. Okay, some of you have not seen. Yeah, so it is for those of you who have not seen. And just to see how snow looks like. And it looks very white as compared to any other part of land surface. So you can see here the snow looks extremely white and surrounding rock how it looks like. So that is the first most striking feature in your mind, that how snow looks like, and then how it gets reflected into its characteristic, reflectance and absorption characteristic is the next step of that. Then how many of you, most of you have seen the ice, I'm sure, if not anywhere else, but at least from your refrigerator. So let us look into the ice, but how it looks in the nature. So not in refrigerator. You can see here, this is ice, huge ice near Samudra Tapu Glacier. It is the terminus of Samudra Tapu Glacier. And you can see how it looks like. It is, I think you can make out very clearly the difference between snow and ice, just looking at it. But this is not the way ice looks into nature. Nature can do many tricks to it, And one of the trick nature can do is drop lot of volcanic ash into it. Okay, so how it looks like? Can you listen? Is it off? All right. Okay, so now when you add the ash into it, its color changes. It looks more darker. So you have now snow, which is extremely white, and it is possible for you to have ice, which is very close to black. So you have what it means. It means it can change its absorption characteristics, right? So how much energy coming from sun, how much it can absorb, will keep on changing depending upon the nature of snow and nature of ice. So that is a trick we are going to use in our analysis and try to put in a more scientific way than the way we are putting. But key question is why we should do it, because many of us who live in Bengaluru, which is the deep south, how does it matter to us, because we have not seen snow. Temperature is very comfortable here, always in 20s, and how does it matter? But if you look into the Himalayas, you can see whatever red, blue, whatever all colors you see, in addition to white, all those colors where there is a huge amount of snow. So you can see entire North India, a Himalayan terrain with Tibetan plateau, part of China, Afghanistan, in Myanmar, in Arunachal Pradesh, there is a huge amount of snow cover is there. And what that snow is doing is an important thing. And you can see here that how much that snow and glacier melts and contributes into our river system. And you can see here that if you take into the Bhakra, the contribution of snow and glacier melt in Bhakra is 59%. So the 59% of water annually coming into the Govind Sagar, which is the name of Bhakra reservoir, 59%. And if you go into the Pakistan side of Indus Basin, this could be high as 72%. And in Pandor Dam, which is further downstream, how many of you are aware of Pandor Dam? Yeah, very few. So when this Satluj or Bias, it is on Bias, when that Bias comes further down and before entering into the Pakistan, there is one more dam, and from where the Indira Gandhi Canal comes out and comes water into the Rajasthan, so it's almost 35%. So you have a huge amount of water which is coming into the crucial summer month into our river system. And when it comes into our river system, as soon as it enters from hills into the plain, there's a huge amount of canal network. You have Upper Ganges Canal, you have Lower Ganges Canal, you have Bhakra Nangal Canal. So all water is diverted, and you can see here is that it is in Pakistan, it is almost 96% of food is grain, food grain is produced in the catchment area of that canal network. So it is a huge. It comes to the India in a Punjab and Haryana, where this water mostly goes, 26%, and food grain production is 37% in parts of Ganga. So overall it is around 60%. So you can see that our dependence on runoff of which is caused due to snow and glacier melt is huge. And our food security and water security can be significantly influenced if there is change in the runoff snow and gelt pattern takes place, if glacier vanishes. It is a major threat to the national security. Therefore, it becomes a huge issue. Many of you are aware, and some of you are working in glaciology projects, because then government realized that we need to do something on this. So that is why this is very important. But some of you have already seen this basic definition, that how it is snow, ice and glacier. Is it now properly explained? All of you are familiar with that. Those who don't know, they can raise their hand. Everybody knows it. Wonderful. So I can skip this. Now this also just now Helgi has told you, so I will skip it. So the key question now let me say here is, what will happen as you have a fresh snow which has a very low density and which is around 50 to 70 kilogram per meter cube, and as it reaches into different categories and it reaches to fur, which is normally considered as 1-year-old snow, and its density is between glacial ice and snow. It is moving around 400 kilograms, and as it becomes glacier ice, it is around 900 kilograms per meter cube. So what will happen to the reflectance characteristic of snow? Because that is where key issue, because now we are talking about the satellite sensors, where we will observe this change from snow to ice, and that is foundation for us to map glacier by using satellite images. So the key property of doing that is refractive index, which Jay has just talked about. I think somebody has rubbed it, but it is there. You have two parts of refractive index. One is the real part, one is imaginary part. And the imaginary part is something which is help us to know the absorption coefficient. So mostly you can see here is it is low. We have very low. Fundamentally, there is no difference between ice and water in certain parts of electromagnetic spectrum, but as wavelength increases, absorption is also increasing, and in a certain region, which is around SWIR, shortwave infrared, the difference becomes large. So that could be the reason where we can differentiate between ice and water, but we are not going into that issue. We are more concentrating on how snow is changing its densities from snow to ice, what it will. But point which is you have to remember is the spectral variation in real part n is small, and the difference between ice and water may not be significant. And another point you should also remember is in visible wavelength k, which is imaginary part of refractive index, is very small and ice is transparent. Right? You got that idea? Anyone has missed this idea from this side? What it means? It means that in visible part of electromagnetic spectrum, what is the range of visible part of electromagnetic spectrum? 0.4 to 0.7. And what is so special about that? No, we can see in it. Okay, so it is a wavelength where our eyes are sensitive. So in this region, k is small. Absorption coefficient is very small. What it means? It means if you have snow and you have incoming solar radiation, it will not be absorbed by ice, correct? It should change its direction a little bit and go down. It should go down to the bottom of snowpack, correct? And the bottom is always soil, correct? So it should, that energy will be absorbed by soil. So why snow should look white? It should look like if you put transparent material on land, it will have the way land looks like. It should look like that. It's because so what else is happening? That is the key thing. So this is, you can see here, is that you have seen this picture. This is now visible part of electromagnetic spectrum, and you can see the soil which has very low reflectance. So if in this visible part of spectrum, entire radiation is going down, eventually it should, snow should look like soil rather than the way we see it. Is that clear? So, but there's something else is happening into it, and it's not only the imaginary part, absorption of solar radiation, but you have also real part of refractive index, where as radiation, incident radiation fall on the snow, there's a change in medium, and the refraction takes place and change in direction. So as it comes from air, it hits the ice crystal, it changes in direction, and then you have in between two snow crystal, there is air over here. Right? That is why it has low density. Otherwise, why it has low density? It is because there is a trapped air in between two ice crystals. And because of that, again it changes its direction. And if there is a multiple times it happens, it changes in such a way that energy gets coming out, it hits here, here again it gets reflected and it comes out. So you have very high reflectance in visible part of spectrum. So as we remove these air spaces in between, because as we increase the density, increase of density can happen only two ways. One way is something has to happen to this, that the volume of ice, snow has to be reduced. That means it has to get out this air. Either it gets out and filled by ice, or it should get out and filled by water. So you have a mixture of whatever it may be. But since what happens is, there is no change in visible part of spectrum, there is no change in imaginary part of refractive index. So you cannot separate out between whether there is a water or whether there is air in it. So what it can do is, as it squeezes, its reflectance starts reducing. So somebody was asking to me whether density, how it influences the reflectance. So as density starts increasing, nothing else happens. Either you remove this air, or what else will happen is, suppose you have a melting daytime, and then night time it freezes. The moment it freezes, because of coalescence, this grain size will increase. It will add another grain to it. So effectively, this grain size will substantially increase. That is how it gets metamorphosed. And that is the process, probably by now you know, eventually snow will convert into the ice. So that is called a freeze and thaw metamorphism or cycle, where daytime it melts, nighttime it freezes, its grain size increases, its density increases up to such an extent over a period of time that it becomes ice. So as it changes, its reflectance collapses, and that is the key for our development. Now, the question is, it's only a phenomenon which we know, but in nature there are a lot of things that are happening. And some of you are asking me about the contamination, but in nature what will happen is, this visible part of spectra, where the density is significantly influencing its reflectance, is also sensitive to numerous impurities which will come with air and it gets deposited on the ice or snow. So you have seen there that there is a drop of volcanic ash. It is not necessary that every time you have a natural phenomena and that dust is thrown into the atmosphere and then it gets deposited. We ourselves are doing it by having so many factories, and nature is also doing, because of the forest fires some places. Then there is a lot of us use fuel for our cooking purposes. Biomass burning is also taking place. So all these things create a small particles which some extent will get move into the atmosphere, and depending upon the prevailing wind condition, it will move towards the glaciers. And what it will do is, it will deposit on the snow or on glaciers, and it will significantly improve its albedo. So you can see here is that most important impurities in snow is atmospheric aerosol and carbon soot. Now, atmospheric aerosol, if you have ever gone to the glacier terrain, and if you have spent the evening, you will realize that suddenly at the evening there is a huge wind start blowing. There is an inversion takes place and there is huge winds start blowing. And if you just sit outside, you will realize that some, sand particles are hitting to your face. You can see that there is so much wind and so much dust particle gets redistributed in very high altitude, around 5,000 meters. So these eventually will get deposited. And you know that it is formed because of, you have very high temperature, when solar radiation hits the rock in the morning, and suddenly it has very cold temperature at night, below freezing, and because of the change in temperature, there is a huge amount of weathering of rock takes place. So what really happens in nature? Nature, the remote sensing, nature has provided some wonderful things for remote sensing scientists, so that they can use this phenomena very intelligently. If you have aerosol and carbon soot, its effect is maximum visible region and declines with increasing wavelength. So as you have certain wavelength around 400 to 700 nanometers, you have maximum influence because of this atmospheric aerosol and carbon soot, and it drops further and it declines up to 1300 nanometers, and beyond 1300 nanometers there is no effect of this aerosol. So trick of the business is, if you have a 2 satellite sensors, which is in range of where you have a visible part in 400 to 700 nanometers, and if it is really getting reflectance have changed, and if you have 1300 nanometer and beyond, if reflectance is not changed, you got the idea that there is carbon soot or atmospheric aerosol in the snow. So you can use it for development of algorithm. That's the idea. So that is one possibility you can do it, and you can see how this idea came here, that you can see as snow effect of contamination on spectral reflectance. So as the soot, which is a small part, is a 10 parts per million, 0.1 parts per million. You can see here poor snow, even small quantities will start affecting the reflectance. And you can see as it can drop quite significantly, and as you move further, it's around 1.1 nanometer, micrometer, or 1300 nanometer, there is absolutely no effect. And it is also, you can see all those, one thing is minute amount of absorption impurities can reduce snow reflectance in visible wavelength, where it is highly transparent. So that is one phenomena we can use to understand whether there is contamination in snow or not. Correct. You have to balance then energy, correct? So if it more absorbs, but we are not working on emission part of this. In theory it will happen, but right now we are not looking into the how emission characteristics of snow. We are looking into the, because emission characteristics come into the picture where depending upon its temperature, is the peak of emission will change, shift. So if it is, so it will shift further down the wavelength. It may go up to thermal band or beyond that, maybe microwave band. Where exactly it will go, we have to see, but it will be much longer wavelength. This emission will take place because emission band is different than reflectance band. So this analysis it will not affect, but you have a point that it may change emission characteristics. This is not part of this. It will not influence this analysis right now. Now, it's not necessary that there is only contamination on surface and nothing else will change in the snowpack. Because snow is extremely dynamic phenomena or a material, it will keep on changing. What it will change is, it will also change as because its grain size. Quite possible that as there is an increase in density, if the area is between two crystals is removed, then it quite effectively they will come very close to each other and there will be coalescence and they can make one large crystal like this. If when they come together, eventually they can make a large crystal because of coalescence. So there is a change in grain size also, right? It's not only snowpack where you have change in contaminants, but there is a change in grain size. But you can see here, what will happen to grain size changes? It is as it changes from 0.05 millimeter to 1 millimeter, you can see here that visible part, which is around, is not significantly affected. But which part which is more affected is the region over here, and one of these bands is the sphere band. So you can, that is why some of you are using, if you have really very nice hyperspectral data, some of are using algorithm to map the grain size. Somebody was talking to me in the afternoon that this unique characteristic you can do. So what is possible now is for us, if you have a satellite data in a right spectral band, it is possible for us to know contamination in the snow. It is possible for us to know the grain size. The two things is possible if you use visible and near infrared solar radiation. Is there anything else is possible? Now, key question is, everybody wants to know whether there is a liquid water in snow or not. Correct? Because it has a profound effect the way snow is going to change. It has very high hydrological significance because if it actually starts melting, it starts producing water which will eventually come into the stream. So if you want to do hydrological analysis, we want to know when the melt season starts and which part of this mountain snow is today melting, so that we can model it and say that tomorrow this much will be our runoff. So everybody has, but unfortunately, what happens is that we have a refractive index between ice and water is very close, except certain other parts of region, particularly microwave. So if you use the visible and near infrared part, you really have very difficulty in estimating liquid water content. You can see here that how dry snow, wet and melting snow, and refrozen snow. So this is, you can see dry snow it has a slightly higher reflectance, and if it is refrozen snow, which is the second graph, its reflectance is reduced, correct? But it is wet snow, and refrozen snow has the same reflectance. What it means? This is crucial for you to understand that you have high reflectance, you have very high reflectance in dry snow, and old snow also, it has changed. But moment it starts melting, wet snow, its reflectance lowers, but when that snowpack again refreezes, its reflectance is not going back to the original value. It is because of the density, and it is also because of permanent change in grain size. Because there is a relationship between as grain size increases. So what it means? As a satellite analysis, if I want to do the satellite analysis and I want to reinterpret it for my algorithm development, what it means? Any other idea? Anything? What it means? The second graph. No, any other idea? Remember, this is in terms of wet, melting snow and frozen snow. Correct. But there is something else conclusion in it. So if I am able to estimate, suppose I have satellite images at periodic interval, correct? And I have a satellite image of 10th of May, suppose, where this is graph, by using your beautiful hyperspectral technique, I estimated this graph. And 12th I got this graph. What it means? It means that when I get this second graph, I don't know whether snow is actually melting or whether it was melting earlier. Right? Sometime it might have melted and refrozen. So we cannot tell the present state of snow in this, because either that snowpack is melting or it might have melted earlier and refrozen now. So I cannot say with guarantee that this is a melting snowpack. So that is the limitation, and you can add some other meteorological observation to overcome that limitation, but this fundamental limitation has to be understood. And you also have to understand is many of you are doing snow cover monitoring, where you are using some of these half-hearted characterization of snowpack, where you have a snow cover estimated by a visible part, and then you take the near infrared part, and the difference you consider as a melting snow. So I have seen the many papers, I get that many papers, and then it automatically gets rejected because you are not saying the difference is a melting snow. So don't make that kind of mistakes. It is a common mistake. Many young people make it that because they read 70s and 80s paper where people have articulated that difference is a melting snow. But in reality, science has grown up, and now we know it is not like that. And of course, this is the one that if you have a density, how density will change, and its albedo, how albedo is going to change with time. So some of you were asking me question that can we estimate age of snow by knowing density? So I will not answer that question. I think I have I have explained to you that how density can change. And remember one thing, that this is age of snow, 20 days, right? And if you extrapolate this graph for entire season, and once it goes and snow gets converted into the ice, then density has no meaning with age. That snow, once it gets converted into ice, it can remain there for thousands of years without changing its density. Right? So, because it cannot change density beyond a point. So, and top of that, the change in density, you can see here, is also a function of time. Look at this. This accumulation season, what it means is a winter time. The change in density is very low because it is only changing because there's some amount of radiation transfer is taking place and between snow and atmosphere, and it is causing change in its grain size, and a little bit compaction is taking place because of that. So the rate of growth of density is extremely slow as compared to the melt season. What happens in melt season is there is a melting and refreezing takes place. It melts during daytime and it freezes during night time. So the rate is very, very fast. So, and that is reflected. So suppose you go to Antarctica and you have a very small amount of snowfall. It may take a couple of 100 years to convert that snow into the ice. And if you come to the Himalaya, when we are having melt and freeze cycle, within a decade it can change into the ice. So we have to realize there is a huge gap between, depending upon what kind of melting processes are taking place. So it is important that this cannot be a powerful tool for us to estimate age because the amount of uncertainty is too large depending upon the meteorological condition of that year, of that region, of various other things. So it's not very powerful tool. Now key question is how deep it can penetrate inside the snowpack. Now we are seeing, because you know that most of the energy transfer between snow and atmosphere, it takes place in only top layer. But key question is how deep it can penetrate and which region of electromagnetic spectrum can penetrate maximum. And that is very important for us to start interpreting the satellite images. Because, and you can see that if we have near infrared or SWIS part of electromagnetic spectrum, which is, you can see here, there is hardly any penetration inside the snowpack of energy. And what it means is most of the energy transfer is taking place at the surface only. So the very thin, few millimeters of snowpack can give you the signature of snow. But if we have a region which is around 500 to 600 nanometer, it can penetrate deep. So a visible part of spectrum can penetrate much deep, and it depends upon, but however, it's almost energy is fast, first 10, most of the energy gets attenuated in a first 10 centimeter. So anything is beyond 10 centimeter can start affecting your reflector. So yeah, of course it will vary. It will vary. This is observation for in Arctic part of Canada. So it is a very dry snow. In the winter it was taken, its density is very low. As its liquid water content, its density changes, then actually its penetration gets reduced very dramatically. So if it is a fresh snowfall and completely dry snowpack, this characteristic will be there. Otherwise, it will change. So this is now with this background. Okay, another 15 minutes, but I want to bring you up to the level where I can have afternoon exercise for you. So, so that after that we can. So key question is now, how do you monitor snow by using satellite images, correct? And now we have series of satellites, there are satellite sensors are there, some are acquiring data every day, some are acquired once in a week, some are acquiring once in a 20 days, and it has a different spatial resolution, it has a different orientation, all kinds of issues are there. So key question is now, our problem is snow cover. We want to develop an algorithm which can monitor snow cover in such a fashion that as far as possible it should be automatic in nature. And it should have unique signature than any other feature on the land. That means it should differentiate water, vegetation, rock, all those features can be separated. So this is snow cover. So algorithm is nothing but is a method expressed as a finite list of well-defined instructions for calculating a function. That means you may not be able to do it one instruction in a computer. You can have 10, 20, 50, 60, 100, whatever it is, but there has to be number. It cannot be infinite. So you require different tricks to apply, and we will come to those tricks slowly and steadily to make sure that you get what we want. And this context is our snow, and this instruction should be unique so that you can estimate snow from other land features as vegetation, rock, soil and water. That should be our idea. It should separate from that. And it should use band or combination of band so that it can have a unique range. So first thing, how many of you have seen the satellite images or handled satellite images? Okay, and how many of you have not handled? Yeah? You have handled? Huh? No, you have not. Anybody else? किसी ने सैटेलाइट डाटा यूज नहीं किया है, वो हाथ करे. आपने यूज किया है सैटेलाइट डाटा? हाथ ऊपर करो फिर. So, okay, I got it. At least some of you have not used. So first thing you get when you download satellite data in your computer, first thing you get is a digital number. Correct? That means its range from 0 to whatever it may be, 250,000, whatever it may be, depending upon bit you get. So that is called the digital number you get. Now, quick question is, what do we do with that? What is that digital number is all about? Okay, we will skip that. Okay, so we get the digital number, and we have seen this curve earlier, and you can look into the snow curve. So you have here visible part here, reflectance is very high, and you come here sphere part, reflectance of snow is very low, here 1500. So if we have a satellite images, the digital number in this band should be very high, and therefore it should look white if it is a black and white picture. And here digital number is very low, therefore it should look black. That is first thing. You look at it and you should conclude and get it. And this you can see here, one imagery, where I RSP3 WIPS data, and you can see here that same region where the snow looks very bright, it has very high digital number, And same snow looks black in a sphere region. That means 1100 to 1300 nanometer region. So we know the sensor is all right. It is giving something which is up to certain extent reliable, and it fits into our understanding of science. So that is first thing. So if now this is a unique thing. Key question is there any feature on the land which has these characteristics? Right? Whether water, vegetation, or any other feature where in visible part we have high reflectance and a sphere part has a low reflectance. So if you plot it, just put the scatter plot. That means there are different techniques on when you start analyzing satellite data. One of that technique is you take the grid, which is visible part of spectrum, and you take sphere, which is 1.55 to 1.75 micrometer of electromagnetic spectrum, and you take features and you plot it, how they look like digital. This is in reflectance, but you just plot it, and what you will see here is they are separated quite significantly. So this is snow, this is the water, this is ice, this is snow under shadow. So what you can see here is, and this is where rock vegetation is there. So they are specially distributed on a two-dimensional graph. So it should be possible for us, by applying some tricks and some analysis, to separate snow from other land features. So that is the first thing you do. Now let us look into satellite sensor, because now we are going to develop algorithm for ABIF sensor. ABIF nothing but advanced wide angle field spectral radiometer, spectrometer, which is in sensor of IRS PIC 6. Now it is on subsequently other sensors. What it means? What are its characteristics? We should be very clear about it. Because, yeah, true. So it has spatial resolution. It has ground sampling distance in meter, what they call in engineering term, and in the scientific term we call it as a spatial resolution. Correct? So what it has 56 meter spatial resolution at nadir, and it has 70 meter spatial resolution of nadir. How many of you understand this? Those who don't understand, raise your hand. You couldn't understand. Okay. Correct. So let me explain for those benefit of those who have not understood. Okay. The first thing to understand that, we need to understand first is swath. Earth, without earth curvature effect. So you have a swath. That means when satellite is moving, how much distance on the earth it can observe. See, if satellite is moving like this it is moving in this direction, swath will be perpendicular to that. So how much this distance satellite is going to observe, which is known as swath. Correct? And satellite is moving like this. Correct? And this distance is 700 and correct? This is 740 kilometers. Now, it will move from center. That means it will have this side 370 odd kilometer, and this side it will be 370 kilometer odd. So it is total, it is 740 kilometers, right? So satellite exactly is here. If my arithmetic is correct, I don't know. It is half of 740. So if you put it down on ground, this is a nadir point. So nadir point is, on that point exactly overhead is a satellite. Correct? And this is off nadir point. Correct? This is off nadir point. So it will, how much distance satellite will see on Earth is a function of, you have a, here is a camera, and camera has a small CCD. Correct? Couple of thousand CCDs are there. Like what you have ordinary cameras in these days where the charge coupled devices are there. Correct? And depending upon its optics and other things, now you have to divide this each CCD in such a fashion that you cover entire 740 kilometers. Right? But the amount of distance will, how much land space it will see, is depending upon how much angle it is doing with the land. So if it is nadir, it will make angle like this. Like this. If it is off nadir, it will make angle like this. So for same solid angle, if it is the same solid angle here, it will look a larger distance if you are looking at across, and if it is looking vertically down, it will look the shorter distance. So you have 56 meter spatial resolution here. Here we have 56 meter, and here we have 70 meter. Now what do you do? Engineers do the trick with this, because if you give to you with this kind of thing, you will be completely lost. Right? Because you say, what is this? Again you have to do some calculations and then estimate. So what they will do the resampling. And there is another issue on this is, there is one more direction also spatial, because this is, you have seen the across, but this is along the track, it is also moving. Correct? So it has to also move in such a fashion that amount of distance this see on ground, it should be able to process and analyze and take another picture. Correct? And that it has to do within a 9.96 milliseconds. Right? So that satellite camera should be ready to take another picture within 9.96 milliseconds, and if it has to do that, depending upon optics and height, it can cover on 66 meter spatial resolution. So you have each pixel, it has a 3 spatial resolution. It has a 2 spatial resolution. One is along the track, one is across the track, which is varying from 56 to 70 meter, depending upon where it is lying on this. Correct? And another direction along track, it will have a 66 meter. And if it doesn't do within this 9.96 milliseconds, there will be gap. So you will see that there are many striations you will see, because sometimes either satellite comes down, and because of down its speed changes, and its electronics and other mechanics doesn't match with it, so there is a gap. Satellite will move very quickly, and it is not ready, so the land is lost in between. So there is a gaps, there is the striations, straps, and other things will come because of this. And then it has the 5 spectral bands. Is it clear? Anybody has confusion on this? Yes, you tell me. Clear? Wonderful. Huh? This is CCD, there is no scanner. There is no mechanical moving devices. There is no scanner. Other sensors like MSS and others, they use the scanner, or TM use the scanner. Here we don't use the scanner. Huh? No, whether it is CCD or whether you use, this is a characteristic of SWAT. In order to, because it's the function of this solid angle. As the solid angle changes, whichever mechanism you use, this problem is bound to be there. As long as you are looking away from that side, this problem will be there, whatever you use. Because this has problem with optics. As you can improve the optics and reduce this, but you cannot eliminate it completely, because at the end of the day, this is a solid angle which is making, and something can be added into it because of the optics, the kind of lens you use. Because as the lens performance reduces as it move on the edges. So you can improve that, but you can never eliminate this problem. Huh? Huh? No, CCD is not moving. CCD, but they are fixed with the angle. And then you have in between optics. In between you have lenses. And each CCD is designed. It's not, everybody is not, everything has given little bit angle so that it see with particular angle. And since it is not moving, it is considered better technology, because in other instrument has to, that mirror has to move to scan it. And if you have more moving parts in the satellite, if something goes wrong, you cannot fix it. Here there is nothing is moving. Therefore, it is considered as a stable instrument. And that is, and now, next question is how many bands it has. It has 5 bands, this sensor. One band is in visible region, is in green, it is in red, in near infrared and far infrared, or sweet band. So there are 5 bands and with spectral difference. What is the meaning of quantization? How many of you know the meaning of quantization? Yeah. So what it means? 10 raised to 2, what it means? Two raised to power 10. So how many pixels, how many digital number it will have? Correct. Yeah, correct. So what it will give you, depending upon quantization, you have number of pixels in satellite images. Correct. So if it is a 7-bit data, you will have pixels numbers from 0 to 2 raised to power 7. If you have 10 bits data, you will have a digital number from 0 to 2 raised to 10 raised to power 10, 2 raised to power 10. So quantization is important. Why you will realize it's not strictly called radiometric resolution. By the time we finish that, you will be able to understand. It is loosely used by people to say that it is a radiometric resolution, but it's not in a stricter sense, because there's another component in it is radian setting. Right? So radian setting is something which you can do with 100%. So key question is how much energy is coming from sun in that band of electromagnetic spectrum. So suppose you have band which is 0.52 to 0.59. How much energy from sun will come? It will vary depending upon season, isn't it? Depending upon location of the earth, latitude, longitude. So, key question is, how much is the solar constant in it? That means how much above the atmosphere, how much maximum radiation, if you have measurement which is perpendicular to the incoming solar radiation, and there is no scattering by atmosphere because we are measured above the atmosphere, and it's only function of sun-earth distance, and it can vary depending upon the angle which sun is making with the measuring plane. So many sensors, if you see, they do not have very high radiance setting. Suppose what will happen? You take the radiance setting of, you will see later on, that these three sensors. I'm just giving arbitrary data that I put it in the 27 microwatt per centimeter square per steradian per micron saturation. I have a 10-bit data, it doesn't matter, but I make it in the 27. What will happen? Anybody has clue? So you have 53 is, and I have set aside at say 27. Correct. So if I plot a graph, that how much is radiance I am getting from the surface, correct? This is the radiance. And if I am getting 10, you will plot it like this. 10, 11, 12, 13, 14, 15. You reach up to 27, and if you get the 28, it will look 27, 29, 27. So any energy which is received by satellite, which value is more than 27, because I have saturation radius is 27, is appear only 27. Correct? That is known as saturation radiance. Key question is, why earlier series of satellites have put this at the lower? I will leave that question for you to contemplate, and we will, if you don't find answer, I will give you tomorrow answer, but think over it, why they have done it. So, coming back to what you were saying earlier, your radiometric resolution will not only depend, even if in this case I have 10 bits data, what it will do? It will only say the maximum value and continue saying even if it is what. So you have not improved your radiometric resolution, you have only improved radiometric resolution in this part. You are not improved in this part. So in that sense, so you have to use in this combination. And then there is another issue of band-to-band registration. That means you have 4 bands. At the end, it is engineering design. One pixel is not straight away going to fix into the another, because sensor has to split it. Because moment radiation comes, it has to split into the there is a grating inside it. The grating means it is a wheel which is rotating inside and which has a different filter. So the moment it sees the one is rotated, green is seen, same is rotated, then other is seen. So it is a grating, that is called grating. So it is rotating wheel. So there is inaccuracies in that, but our registration should be 0.25. That means one pixel when we have, if you fix it in another pixel, it should be off by 25%. Maximum it is allowed. You cannot have 100% matching. We presume it is 100% matching, but 25% if it is off, then it is accepted. Why this is important? This is important because when you start doing analysis, you should know, because many of you come up with one pixel saying that this pixel has this grain size, this pixel has this another grain size, without realizing all these limitations. So what we will do is, we will stop here, and we will discuss tomorrow on next step, how we are going to see it. But there is also, we will have in the afternoon class where exercise where we will estimate basically all these things, influence, how to convert digital number into the reflectors. So maybe what I will do is I will continue with the talk for another half an hour in afternoon, and then I will give you the exercise so that you will understand the science behind this properly. So all of you, what you need is if you have a computer, in afternoon it is wonderful. If you don't have a computer, you should be able to do with the scientific calculator this exercise. But you do it so that you will understand how it is done in very differently in a computer. Same thing, you can do it for few pixels and get it. Right? So we can have lunch now and relax for some more time and get back to around 2 o'clock. If you have any questions, you can ask me now or during lunch also. It is given by a sensor. It is
to ask